Okay, you might be familiar with the so-called method of exhaustion, which is a way to, we have some more complicated geometric figure, and we want to make measurements, its area, perimeter, whatever. And the way that one of the ways we can do that is by approximating it with simpler geometric objects, and then computing the corresponding geometric measurement of that simpler object. And then in modern language, you would say, taking the limit as these simpler geometric objects somehow fill up or become the more complicated one that we're looking at. So a common one is you want to take like a circle and you want to compute its area. You approximate it with regular polygons. You compute the area of each one of those polygons, and as n goes to infinity, that is the number of sides goes to infinity, the area of the polygons should approach the area of the circle. Now geometrically this makes a lot of sense because the two things are becoming each other. The sequence of polygons is in some sense converging to a circle, whatever that might mean in this context. And so it seems intuitively clear that the corresponding measurements will also converge to each other. But there actually needs to be a little bit of more of an argument to get that last step, that the geometric measurements of the sequence of regular shapes approaches the corresponding geometric measurements of whatever it is we care about. And I'm going to give you an example using something that is familiar. Maybe it'll make you ask some questions. Hopefully this will make you ask some questions. It's going to be a very familiar topic from calculus, but it's not one that we explain very well. Right? I shouldn't say we. It's not something that when I teach calculus, I explain very well, and I don't know if I've ever explained it when I've taught calculus. Okay, I don't teach calculus a whole lot, but I definitely have not done this when I've taught calculus. Okay, so without further ado, let's consider the following problem. We're going to look at an increasing function. It doesn't matter which one. I want to keep things kind of generic here. And the only properties that it has is going to be continuous. It's going to go from 0 to 1. It's going to start at 0 and go up to 1 like this. So this point here is, so 0 to 1 here, 0 to 1 here, a continuous increasing function. That's pretty much the only properties that this needs to have to explain to you a problem with the method of exhaustion. Now, how do we compute the area under the curve? Well, the common calculus way is to divide this up into n evenly spaced intervals, and I'm going to look at the right-hand endpoints like this. Sorry, I'm going to color code these a little bit differently. You'll see why in just a moment. So we're going to get something like this. That'll be that side of the rectangles. Then we'll have this, like that. Again, I'm color coding these for a reason that will hopefully become clear by the end of the video. And then let me make these purple. Okay, now we know that as n goes to infinity, or at least we've been told in calculus, that as n goes to infinity, that is a number of subintervals here, goes to infinity, that these rectangles, the area of these rectangles is going to approach the area under the curve. Okay, now, like I said, I've not seen this rigorously proven in calculus just because it is not something that can be done using the things that are known in calculus. Typically, it's not something that can be done using the things that are known in calculus, and to even give sort of an argument related or similar to the stuff we're going to talk about this week would take the class too far afield. But here's what I want to ask. So we know that the area of these rectangles approaches the area under the curve. That is, we can compute each one of these, the area of each one of these rectangles, add them together. For every n, we get an estimate, and as n goes to infinity, that area goes to the area under the curve. Okay, but I want to ask the question: what about the perimeter of this shape? So let's say I have a shape, and its base is this. It's got this and that. I want to compute the area. So, or I want to compute the perimeter of that shape. So the question is, can I use the perimeter of these rectangles? So these rectangles are a shape. If I forget about these blue lines right here, the question is, as n goes to infinity, do the perimeter of these rectangles go to the perimeter of this shape here? Okay, because that's what the method of exhaustion kind of implies. When we have a sequence of geometric shapes with known measurements, that those measurements are going to and if those geometric shapes converge to a different shape, then the corresponding geometric measurements should converge. So let's think about this. Let's compute the perimeter of these rectangles here. Well, we're going to have, when I say the rectangles, I mean this whole thing here. So we've got the base of the rectangles. The base of the rectangles, if you add them all up, that plus that plus that plus that plus that, it equals to 1. It equals 1. If you add up this parameter here, or this line segment there, that has length 1. Let's think about the green line segments. So the green line segments are going to go from there to there to there to there to there. So notice they all add up to 1. You're going to go from there to there, there to there, there to there, there to there. They're just the bases but shifted up. Okay, so that's also, the green ones are also going to add up to 1. Now what about the purple ones? The purple ones aren't, the purple ones are on the side here, and if we kind of extend them over here, and this one gets extended like this, that, and so on and so forth, they're going to add up to all of these, whatever that adds up to be. And that's going to be 1 minus something small. So this right here, as n goes to infinity, I'm going to call this, as n goes to infinity, I'm going to call this, I'm going to call this distance epsilon, because as n goes to infinity, this is going to come down that way, and that's going to get smaller and smaller and smaller. So it goes to 1 minus epsilon. Okay, so overall, the perimeter of the rectangles is 1, 1, 1, 1 minus epsilon. So it's 4 minus epsilon. And this is approximately going to be equal to 4. You can get it within 4 as much as you want. By taking n large enough, you can get this as close to 4 as you want. So the perimeter of the rectangles is converging to 4. The perimeter of this shape is converging to 4. But that is definitely not going to be what's happening with the perimeter of this shape here. Because notice that the only thing that we're using is just that we have an increasing function. So this function, a straight line, that's also an increasing function. And so the same argument would apply here. The approximating rectangles for this triangular shape here is going to converge to 4 as well. So it doesn't matter. The perimeter of the approximating rectangles is going to converge to 4 no matter what the function is, as long as it's an increasing function. If it's decreasing, it'll, well, the more argument is needed to compute what is going to converge to. But anyways, the point is that the perimeter does not converge. The perimeter of the approximating shapes does not converge to the perimeter of the shape that is approximating. So the question is, well, it's not really a question. Well, one question is that you can answer in the discussions is why is that? But then the worry is now when we look at Archimedes' way of doing this method of exhaustion, why does whatever's going on here not go on with what he's doing? And the answer is he just makes a slightly more rigorous argument.